Okay, let's continue. So you have this as a sufficient statistic. And the next step is to find a solution of the sufficient statistic that produce unbiased estimator. So if we recall the Fisher factorization theorem, we are aware that this is the term for H, and then there's a term for G, but G is supposed to be the estimator. Okay, so assume P of X is a complete sufficient statistic. To do so, we need to find a function G such that the expect, notice this expect of sufficient statistic is equal to A for all A larger than 0. Okay, but since if you do expectation for x squared, it will be n e expect x squared equal to n. Expect squared is what? Is the second moment, right? That's the second moment. So the second moment is equal to the variance plus expect of square xn. Then it will be, this is doable, right? This is doable. So it will be A. How come? If you come back to see this, if you come back a little bit and see this, x squared is, if you take the expectation of x squared, you are going to get the variance of w, but the variance of w is A, right? So you get this equal to that, and you get expect of x squared. Expect of x is equal to A. As a result, you take the square, you get this. So at this, up to this point, it's not obvious how we choose G. We cannot simply scale a sufficient statistic to make it unbiased. All right, so we have a little bit of trouble, right? We have a trouble here. Then the second approach is to determine the conditional expectation. Expect of, this is the second procedure we mentioned in chapter 5. Expect of A, condition on summation of x squared, where A hat is any unbiased estimator. So if we were to choose the unbiased estimator equal to this, the NVU estimator will take the form like this. Unfortunately, the evaluation of the conditional expectation appears to be formidable task. Formidable task means that 很复杂，算不太出来的那一种数学式。Okay, it's a bit intractable. So if we want to take this, it's not tractable. So we now have to exhaust our possible optimal procedure approaches. This is not to say that we could not propose some estimators. One possibility considers A to be the mean, so that A1 hat is equal to this. Now, since we know that A is larger than 0, another estimator considers A to be variance to yield this. So what are we doing here? What we are doing here is, it may seem a little bit confusing for you because you see this for the first time. Oftentimes when we do estimator design, we are actually doing conjectures. We're doing conjectures. So, uh, so one conjecture is that if x is equal to a plus a noise, then uh, taking the mean of the sample seems to be something reasonable, right? It's not reasonable, totally reasonable, because it's also in the variance of a, but uh, in the variance of w. I'm sorry, but if you don't have other approaches to make a conjecture for taking the average of the sample, seems to be a possibility. Okay, and the next thing is we want to do variance A. If it's a variance of A, you already get A1. Then how about let's do A2 head equal to the estimated for the variance, except it has to be subtracted by A1 head. Okay, so all we are doing here is to make some guesses or conjectures. Okay, uh, so we can only say this is a possibility, a possible choice for our A。那这一段比较抽象，我再稍微用中文观念讲一下，就是我们已经尝试了两个方法，对不对？一个方法是 Fisher，是这个 Fisher factorization 的方法，但是要找到 unbiased 的一个 term 相当的难，因为 take expectation 要让它等于 a 这件事并不容易。我们 take x square 发现它是一个会有二阶的 a 函数在里面，所以不太能够说我们用一个加减乘除的简单的加减乘除就把 g of x summation square 等于 a 这个 expectation 的 term 找出来。所以 Fisher 的方法 ，Fisher factorization 的方法，很显然有困难的。那第二个方法就是用这个找一个 MVU 放在 expectation 的这个所谓 second approach，第五章讲的 second approach。那很显然的也算不太出来，所以接下来怎么办呢？系统性的方法都找不太出来了。那我们就会尝试说开始做一些猜测。那这个猜测呢，猜测或猜想的conjecture， 这个是在 estimator 的设计或寻找的过程里面，有时候你标准的方法找不到的时候，我们会尝试去用的一些方法，从猜测里面去寻找看看有没有好的 estimator。如果有的话，或者很接近的话，那我们做一些调整，我们就找到了这样。但是还是有可能我们的猜测是不太好的，所以一直找不到。这就是这门课呃，应该是说要给各位同学最重要的观念：estimator 的设计并不是一件 trivial 的事情，它是一个简单的话就很快找到，就 Fisher 的方法就找到了，或者是加减乘除就找到了。那如果复杂的话，就像这一题一样，就一直找不到这样。那我们就用一些猜测，比如说我们猜测 A1 等于什么，然后 A2 再用一个 as a function of data and A1 的方式去找找看这样子。那但是结论先讲，就是说这些方法还是不是 optimal。好，那在 Problem 7.2里面有讲的。Okay, so faced with the inability to find MVU, we will propose an estimate that are approximately optimal. We claim that for large data records, as for n approaches infinity, the proposed estimator is efficient. This means that n when n is approaching in infinity, then expect of a head is approaching a, variance of a is approaching CRLB。所以重要的观念就是说，如果这个在 limited data 的 scenario 你找不到，我们是不是可以找一个 n 的值够大的时候，它接近 optimal 啊？什么叫接近 optimal？ 接近 optimal 就是 unbiased， 所以就是这个第一个。那 variance 角度来看 optimal 就是要它 approach CRLB。OK， so okay, so as I say, we made some conjectures. So we propose the following estimator: A head is equal to 1 minus 1 over 2 plus this. You want to be aware that this is not trivial, right? How and what does a person do to be able to come up with this estimator? It's totally non-trivial, and it could be someone make a conjecture, and it happens to be his solution happens to be close to optimal. Okay, that would be, in some sense, we will say that there is part of luck, good luck, and good intuition in that process. Okay, so but uh, regarding how it comes up, let's take a look at if this is given, then what's going to happen. Okay, so if this is given, then this estimator is biased because you take the expectation, and expectation becomes this and this, and then for all A, I'm sorry, it's this. But as you know, expect of this is this, but expect of this, can you just put the expectation into a square root? The answer is no, right? Expect of a function of a random variable is not equal to function of expectation of the random variable. It's not interchangeable. But let's see, if we put expectation into it, then the outcome is going to be A, and we know that this is inequality. As a result, we can claim that expect of A hat is not equal to A. So it's biased. It is nonetheless a reasonable estimator in that as n approaches infinity, we have by law of large numbers, this is approaching this. This is called law of large number, yeah, right, law of large number. 就是 sample mean 会趋近于它的期望值，这是 law of large number 讲的。OK， 所以这个就趋近期望值 is equal to this, and therefore A hat is approaching A. Okay, A hat, because E expect of x squared is equal to this. Then you put this in. You put this in what? In where? In here. In here, then this inequality becomes equality. 就是不等式会变成等式嘛，哈，把这个放进来的话，放进这里，这个不等，放进这里，这个不等式会变成等式，所以就 expect the A hat 就变成 A 了。Then, we will see that to happen, and then the estimator A hat is said to be a consistent estimator. To find the mean and variance as n approaches infinity, we use the statistical linearization argument described for this PDF of this will be concentrated about its mean for large data records. This allows us to linearize a function given in this 7.6 that transforms this into A. Let G be the function so that A hat is equal to G. But A hat is what? A hat is already been given here, right? Already been given. So this is just a change of notation. We do summation of this equal to U, and therefore G of U is equal to this. And linearize it around this. This is the first order Taylor expansion. Taylor 展开式，然后只保留第一项，就是这个。Okay, so you get A hat equal to A plus this. This is the Taylor expansion. And U is what? U is this, right? U is this. So U is this, then you put U, you change U into a function of data, then it recovers this whole function into this. Now it follows that asymptotic mean is this. Asymptotic means when n approaches infinity, so that A hat is asymptotically unbiased. Additionally, the asymptotic variance becomes this, right? And then, but this has a variance of this, but variance of this can be shown to be that. And how come? If you go back to the signal model, you take the variance of this, you take the variance of that square, of course, square, not only x but x squared. Then you get something like that, and then you put it in, you do simplification, you get that. So, so now we get uh, asymptotic mean equal to a, and we get variance of a. So now we are kind of happy about it because we have a unbiased estimator asymptotically, of course, and also its variance and its mean. It's mean to be unbiased. Okay, so so let's take a look at this, and this term happens to be CILB. CILB. So summarizing our results, the proposed estimator given by this is asymptotically unbiased and asymptotically achieves the CIRB. So at least we say that it's asymptotically efficient. And for limited data, we may not be able to come up with a beautiful estimator, but for asymptotic case, which means n approaches infinity, we at least find something reasonably good. It's reasonable because it's asymptotically achieves CRLB and then asymptotically unbiased. Okay, so that's the end of this session, and we'll continue next session.